Welcome to this module on Einstein's theory of special relativity. Now, to set the stage in this lecture, let's review somewhat Newtonian physics, and in particular, Newtonian relativity. Right. So, Galileo and Newton described the motion of objects with respect to a particular reference frame, which is basically a coordinate system attached to a particular observer. So you have a location, say in this coordinate system, this dot, and you can measure it in terms of x and y, the coordinate system that's attached to the reference frame, that is the frame where you're doing the measurement. Now, a reference frame in which Newton's laws hold is called an inertial frame. And it turns out that must be a frame that is not accelerating. If you're accelerating, the laws of physics would look different in that particular reference frame. Basically, things that should be at rest will look like they're accelerating down or up, for example. Now, one can consider a Newtonian principle of relativity, also known as Galilean invariance, which is that if Newton's laws hold in one inertial frame, they also hold in another reference frame moving at a constant velocity relative to the first frame. So that other frame is also an inertial frame. Okay, so if you've got the laws of physics holding in one reference frame, that's known as an inertial frame, and there's another one moving at a constant velocity with respect to it, that other frame that appears to be moving by you at a constant velocity is also an inertial frame, and also Newton's laws hold in that one. So let's discuss a bit how to do a transformation from one reference frame to another, one inertial frame that is, to another. And so that's known as a Galilean transformation. So let's say I've got my reference frame, and I'm going to label that reference frame S. In other books or sources you might see it labeled with an O for observer, but I'll call my reference frames S. So in this reference frame, I've got coordinate system x and y attached to it, and there's some location on it. Okay. Now, let's suppose a car is going to drive by this reference frame. Now, the car itself, you can imagine having a reference frame attached to it as well. So let's let that car go across the screen. So it's moving at some constant velocity by my reference frame S. So let's go back a moment. And let's attach another reference frame S prime to the car's reference frame. And that is the frame that's going to move by the reference frame S. Right? So if I set it in motion and I talk about a location in frame S prime, that frame is moving by frame S. So what is a Galilean transformation? Well, I would like to relate the coordinates, say in this frame S prime, the moving frame, the one that was attached to a car, relative to the coordinates in frame S. Maybe that's on the side of the road where I had coordinates x and y instead of x prime and y prime. So how would I write down those coordinates? Well, first of all, let's label the speed with which frame S prime moves by frame S as speed v. And it's a velocity vector, so I'm going to give it a direction. I'm going to put it along the x-axis. And I'm going to let the x prime and x-axes coincide. And so I want to transform from frame S prime to frame S for each of the three coordinates, spatial coordinates. Well, what I can see is if I've got a coordinate in frame S prime, if I look at the x coordinate, that's coordinate x prime, I know this frame is moving at speed v relative to frame S, so I know velocity times time, if I add that distance, velocity times time, to x prime, that'll be the coordinate in frame S. Okay. So I can write that x, the coordinate in frame S, is just x prime plus vt prime. Now, there's an assumption here, which is that the origins of these two coordinate systems overlapped at time t equals 0, or time t prime equals 0. What about the perpendicular coordinates, y and y prime? Well, the reference frame S prime was moving parallel to the x-axis. It didn't really change anything about the perpendicular direction y or y prime, right? So we will say those are the same. Likewise, if we could see the third dimension, which would be coming out of the screen, z and z prime are the same. Those are the spatial coordinates and their transformations. Now, in relativity, we're also going to talk about time. What can we say about time? Well, in Newtonian physics, or in Galilean physics, time is universal. And so the time in reference frame S is the same as the time in reference frame t prime. In other words, you can consider there's a master clock, maybe a clock of the universe, and all frames observe that same time. We'll see later, though, that that assumption is wrong. Okay, what if you want to go the other way around? This was transforming from a coordinate in this green frame S prime to a coordinate in frame S, and we saw in the x direction we had to add velocity times time to the position to get the position in frame S. What about the other way around? What if I had a coordinate in frame S and I want to get in S prime? Well, all you really need to do is subtract instead of add velocity times time. We have to have symmetric expressions because the laws of physics should look the same in each inertial frame. The only thing that can change is kind of the relative velocity of one frame to another. So basically, if I have the coordinate in x, if I subtract off velocity times time, that's the distance this frame S prime is moving away from S, then I should get the coordinate in frame S prime. I should get x prime. So x prime is x minus vt. Once again, the transverse directions, y prime and z prime, are unaffected, and these are just the directions perpendicular to the direction of motion. I just chose the x-axis, but remember it's always the direction perpendicular to the motion that is unaffected. And again, universal time here. Time t prime equals t. Okay, so that's how I'm going to transform from one reference frame to the next, and hopefully that was a simple review for you from introductory physics. Now let's talk about how we add velocities going from one frame to the next. So let's talk about adding velocities. So suppose I have two frames, my frame S prime, which has prime coordinates, and again that S prime frame is going to be the frame, say, with a car. Now let's suppose you're in that frame S prime, the one with the one attached to the car, or perhaps more interestingly, a frame attached to a rocket, and you consider tossing a ball forward from the moving car. Or in the case of the space analogy, imagine one booster rocket lets loose a probe, which also has a rocket engine, and it's going to be thrown forward. What would be the velocity of the thing you throw forward, the ball from the car, or the probe from the booster rocket, in the reference frame of the road, or in the case of the rocket, the Earth? So we're going to take that car and we're going to throw a ball forward, and so we can talk about the speed of the ball that you've thrown forward in that frame S prime. Now I've already used v to be the speed of the frame relative to frame S prime relative to S. So I don't want to have too many labels of v, so I'm going to use u. So u prime is the speed, u prime x even, is the speed along the x direction in frame S prime. So ux prime. So I'm going to use u instead of v so we don't mix up those two velocities. This is just the speed of the ball thrown forward relative to the car in that green reference frame. Okay. Now, let's remind ourselves of the Galilean transformation. If I know the position in frame S prime, I can get the position in frame S by just adding velocity times time. X prime is x is x prime plus vt prime. All right. Let's take a derivative of both sides of the equation. Derivative of dx is dx dt. Derivative of x prime is dx prime dt. And then derivative of t prime, but since t prime is t, is just going to be 1, and then times the v just gives me v. So just reinterpreting those derivatives, dx dt is what we call velocity. So that's the velocity in frame S. And so I'll call that ux without the prime. And what was dx prime dt? That's the velocity in frame S prime. So I'll call that ux prime. That's the label I attached there to the car. And then I have plus v, the speed of the object, the speed of the frame relative to the other frame S. And so that's our formula. It's quite simple. It just says, if I want the velocity of the ball thrown forward in frame S, say the frame of the road, it's just the sum of the velocity with respect to the car in the car's frame plus the velocity of the car frame relative to the other frame, right? Ux prime plus v. Quite simple. The trouble is going to come when we let these speeds start to approach that of the speed of light. Okay, so that's all I wanted to say about the Galilean transformation. Let's skip ahead into Newtonian physics and talk a little bit about some other topics, in particular waves, sound waves, and also electromagnetism. So let's start first with sound waves. What are sound waves? Sound waves are longitudinal pressure waves that propagate through matter, like air. Okay? So just to give an example here, imagine I have some cylinder, some piston, and it's filled with some gas, and I've got a wave, which I represent by these brown lines, propagating down this cylinder, and the cylinder has a cross-sectional area A. Well, what a sound wave is a pressure wave. I have a pressure P, say, on one side of this region where I have this dot, and I have a different pressure, slightly different, P plus delta P, a change in pressure on the other side. And it's that pressure change which can propagate through air. So we're not going to go over the whole lecture of how to derive this equation for sound waves. I invite you to look back at those lectures, excuse me, or that chapter in your introductory physics book. But let's just summarize the results. The results are that this change in pressure propagates as a function of space and time, let's say along the x-axis, x and t. So it's just a change in the pressure. There's obviously some ambient pressure, but we're talking about the change in pressure which can propagate through air as you hear my sound through the air. And so it'll have some magnitude, and then it'll have a sinusoidally varying function, which I represent as sine of kx plus or minus omega t plus a phase angle phi. The plus or minus just has to do with which direction the wave moves. K is what's known as the wave number, and omega is the angular frequency. And the speed of these waves can be calculated because I can rewrite this expression kx plus or minus omega t and write it a different way and say this also equals delta pm, the magnitude of the amplitude, sine of k, and then times the quantity x plus or minus vt, where v is a velocity, and then plus a phase angle. This is a little bit more informative, this form. It's exactly the same here, but v is the velocity of the wave propagation, the sound wave. And it turns out, if you do the essentially the F equals ma, the Newtonian physics to solve for these pressure waves, that velocity depends on the square root of something called the bulk modulus of the material, how stiff it is basically, over its mass density, how many kilograms per cubic meter. So in other words, it depends on the properties of the matter the sound is propagating in. For air, at standard temperature and pressure, which means 20 degrees Celsius and 1 atmosphere of pressure, or about 10 to the 5th pascals, this velocity comes out to be 343 meters per second, or in, say, English units, 765 miles per hour. So pretty fast, right? Now, this sound propagates at this speed relative to the air, to the matter, not the source. What do I mean by that? The sound is a phenomenon propagating through the ambient air, or whatever the matter is, could be water. It's not the speed relative to the source, the emitter of the sound. So I've got some speaker, and that's emitting the sound. It's not moving at 343 meters per second relative to that speaker. It's once it's emitted, it's propagating in the air or in the water. And in fact, if you go fast enough, like the 765 miles per hour, you could catch up to the sound wave and even break that speed, and that's called breaking the sound barrier. Now, what happens if you take away the matter? Well, without matter, as in, for example, space, to borrow from some horror sci-fi movies, no one can hear you scream. There's no sound. Take away the matter, sound does not propagate. Good. So how does this relate to the next topic? Well, let's talk about another source of waves. electromagnetic wave. So now we're going to skip ahead. We're talking physics 2 in introductory physics. And we're going to talk about the solutions to Maxwell's equations, which give you traveling waves also, just like sound, which I've shown schematically here, a sinusoidally varying function. But now, instead of a pressure wave, we're talking about waves in the electric field as a function of space and time, and the magnetic field as a function of space and time. Now again, we're going to skip all the details of how you get these equations, these solutions out of Maxwell's equations. Again, I invite you to review those sections in your introductory physics textbook or other lectures. But again, it's a sinusoidally varying function. I'm going to use the same form I used before, sine of kx plus or minus omega t minus a phase angle phi. It's probably in 3 dimensions, so I wrote it as a scalar dot product, k vector dot x vector. But they're traveling wave solutions. Now, what are all these parameters? So, out front is the magnitude of the electric and magnetic fields. EM and BM are vectors, and they're the amplitude of the electric and magnetic fields. As I said earlier, omega is the angular frequency measured in radians per second. That's 2 pi times f, where f is a so-called cyclic frequency, or just frequency for short. For completeness, the period is just 1 over that cyclic frequency, 1 over f, and that's measured in seconds. K here is the angular wave number. It's 2 pi over a wavelength, where a wavelength is the length between crests. Now, before I go on, let me just show you on the graph to the right some of these quantities. So this amplitude here, that's just the relative maximum height, of the wave, say for the electric field. This is the strength of the electric field. EM would be its maximum value here. We take the absolute value, so it's the same amount down in the maximum downward direction. And that wavelength, which is where I stopped, that's the distance from one peak to the next for this sinusoidally varying function. Now, very importantly, this is not just a fixed electromagnetic sinusoidal wave or field. It's actually moving in time. Okay? So it's moving here. In this case, moving to the right. And so it has a speed, which can be given by the angular frequency over the angular wave number. But from Maxwell's equations, it's 1 over the square root epsilon naught times mu naught. And we're going to call that constant c, and that's the phase velocity of the wave. All right, and I've skipped here, but phi is this phase angle, which just tells you how much offset the peak is relative to, say, the origin. But from Maxwell's equations, the Maxwell's equations are based on basically electromagnetic laws. From the electromagnetic laws, we learned that epsilon naught is the permittivity of free space, and that is 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Mu naught is 4 pi times 10 to the minus 7 Newton second squared per meter squared. And so if I plug that into this expression here, I get that this phase velocity of the wave, which I call c, is 2.998 times 10 to the 8th meters per second. Or we'll just round this to 3 times 10 to the 8th meters per second. That's a large speed, right? That's 300 million meters per second. And so the speed of light is much faster than the speed of sound. And this is a very firm prediction of Maxwell's equations, that the electromagnetic waves, of which light is part of, travels at this enormous speed. Okay, but it makes a firm prediction of exactly this speed, not a range of speeds, and it doesn't seem to depend on, certainly not on the properties of air, for example. Okay, so I'm going to end here on this review. The next lecture to watch is going to be a demonstration of the speed of light traveling in a laboratory, as well as how light can propagate without air in a vacuum. And then we'll pick up from there.